Hi, I'm Xishen. Today I'm going to present our work, Learning Co-segmentation by Segment Swapping for Retrieval and Discovery. This work is done with Ayosha Ifras, Ahmed Yunan, and Mathieu Aubry. In this work, we are interested in the co-segmentation problem, which aims at finding repeated visual details in a pair of images. The problem can be formulated to have a binary mask prediction for each single image, where unmasked regions are repeated patterns. One example of a pair of images is shown in these slides. We use the transparency to highlight repeated patterns. As we want to learn a model to give us such prediction, the main challenge to solve this task is that there is no training data available to train the model. In this work, we propose a solution including training data generation and architectures to address the problem. Here is the plan of this talk. I will start with our key idea, co-segmentation by segment swapping. Then I will show that our approach can be applied to image retrieval tasks. In the third section, I will show that our approach can be used to conduct discovery and co-segmentation on a collection of images. Finally, I will conclude and give a brief summary to our work. Okay, let me first present our approach. Our key idea is to generate synthetic training pairs with duplicated patterns, which allows learning co-segmentation. Precisely, we take annotated segments from COCO and randomly sample a background image. If we directly copy-paste the selected segments, the generated image has obvious artifact. Network can easily support segments through some simple clues, such as the gradient of the boundary, while this information cannot be generalized well on real testing cases. To alleviate the artifact, we propose to leverage boson blending and style transfer on the generated image, which leads to pairs that are more natural on the boundary and potentially harder for the network. Finally, our blending will generate a pair of images containing repeated segments. As a result, we also have access to the mask annotations and the correspondences of the segments. Here are some generated pairs. We show the source image, blended image, and both images with style transfer in the slides. We choose to blend one or two objects such that we are able to learn more complicated displacement field. Instead of using segments annotated in COCO, we also explore advanced unsupervised segments. For unsupervised segments, more details can be found in the paper. To learn co-segmentation, we extract CNN features from the input images and conduct experiments using two different architectures, cross-image transformer and sparse and CNET. For both architectures, the input is a pair of images, and the output contains mask predictions and correspondences mapped for each image. For cross-image transformer, we have two modules, self-attention and cross-attention. Self-attention is the standard attention mechanism and compute attention only in one image with considering position encoding, where cross-attention compute attention in a pair of images without using position encoding. Sparse and CNET compute correlations between two feature maps. These correlations are resized to 40 tensors that can be processed with 40 convolutions. For both architectures, we supervise the training with the mask and correspondences annotations. The objective function is shown in the slides and contains three terms. Here, M and C correspond to the mask and correspondences respectively. The first term is the cross-entropy loss between the predicted and ground truth mask. The last term corresponds to the L1 loss of the correspondences on the repeated regions. In the middle, we add a loss to connect the mask prediction and correspondences prediction, which is the cross-entropy loss on the transported mask wrapped using the predicted correspondences. The output of the network can be used to perform retrieval tasks. We evaluate the performance on Bruegel for one-shot detection. The goal is to identify the same visual details in a database as in a query. We define a score between a pair of images. The score contains joint mask term and feature similarity term. The joint mask term is the product between the transported mask and the predicted mask on the source image. The feature similarity term corresponds to the cosine similarity between a pair of features defined by the predicted correspondences. Here are some visual results. We show the predicted masks as a transparency. We can see in the first row, even there are multiple objects repeated, our approach managed to spot repeated segments. In the second row, the repeated cuts are in different contexts and in small scales. Our approach can still give reasonable prediction. Quantitatively, we report performance for both retrieval and detection. For detection, we obtain bounding box by first cropping a big patch around the predicted correspondences, then computing cosine similarity on sliding window proposals. We employ features trained with MoCo, a CNN feature extractor. For retrieval, both the cross-image transformer and sparse NCNet outperform previous approaches by an important margin. For detection, we find that the predicted correspondences of transformer are more precise and leads to superior performance compared to previous approaches. Note that previous approach leverages multi-scale feature matching and ransack, which is more complicated. Our approach is simpler and better. We also conduct experiments using unsupervised segments, which achieves comparable performance. These results suggest that our approach is not relied on the COCO annotations. Our approach can also be used for place recognition. We conduct experiments on Pittsburgh and Tokyo datasets. The Pittsburgh dataset is a large-scale dataset with more than 10,000 database images and 8,000 queries. The Tokyo dataset is particularly challenging, as the queries are taken in nighttime, while the database images are in daytime. Here are some visual results using our models trained on synthetic pairs, which demonstrate a good generalization on both datasets. Quantitatively, we also achieve comparable performance compared to state-of-the-art approaches. This result is especially impressive, since its benchmarks are very competitive and many dedicated methods leverage geo-referenced images or real correspondences for supervision. On the contrary, our approach is generic and relies solely on our synthetic segment swapping training. Note that we also conducted detailed analysis on the architectures and losses, which can be found in our project page. Instead of focusing on identifying repeated segments from pairs, in this work, we also explore how to perform discovery on a collection of images. Our solution relies on the predicted masks and correspondences to build a graph and formulate the discovery as a clustering problem on the correspondences. Precisely, we build a graph where the nodes are correspondences. Here V is a set containing correspondences. We show the S nodes in the slides. The nodes can be properly defined with the indexes of the source and target image Si and Ti. Predicted correspondences XSI and XTI. Finally, the mask prediction Mi. The edges are consistency between the nodes. Precisely, we consider 3-cycle consistency. We only connect the correspondences which have exactly one image in common. Here are 2 nodes, which are 2 correspondences. Let's assume the correspondences I and J are both connected to image S. The formula is shown on the top, which seems to be complicated, but the concept is simple. We take into account both mask predictions and only connect the edges that the distance in the shared images are closed. We then consider the 3 cycles with XSJ, XTI, and XTJ. We transform XTJ to image Ti using the predicted correspondences from Tj to Ti. And we measure the distance between the transformed position and XTI. The same operation is for XTI. We transform XTI to image Tj using the predicted correspondences from Ti to Tj. And we measure the distance between the transformed position and XTJ. Given the correspondences graph, we use the spectral decomposition of its adjacence matrix to obtain clusters of correspondences for discovery. Precisely, We first compute n principal eigenvectors, then perform k-means with k clusters. To reduce number of nodes in the graph, we use mask predictions to remove the nodes and correspondences that are with low confidence. Some discovered clusters on Bruegel are visualized here. As we can see, the discovered patterns are not necessarily silent objects. They're also with diverse styles and different contexts. More results can be found in the project page. Apart from application on artworks, our approach also achieves competitive performance on object discovery benchmark, which again demonstrates the robustness of our approach. To summarize, in this work, we show that it's possible to learn co-segmentation with only synthetic pairs. We show the model trained on synthetic pairs work well on retrieval tasks. We also introduce correspondences graph for discovery and achieve competitive performance on object discovery benchmarks. Note that our code, data, and more experimental results are available in our project page. Thanks for your attention.